The first speaker from Brazil. The topic is conductivity and the transmittance enhancement of PEDOT PSS thin films by graphene addition from University of São Paulo.
Hello, good afternoon. My name is Felipe. I'm from the University of São Paulo, Brazil, and my work is entitled Conductivity and Transmittance Enhancement of PEDOT PSS thin films by graphene addition. So I'll try to be quick. Organic electronics has gained much attention recently, and one of the materials that should be substituted in this field is indium tin oxide, because it is a fragile material, it is expensive, and one of the candidates to substitute this material is PEDOT PSS, which is a polymeric blend, but it's not as conductive as we would want. So one of the ways to enhance its electrical properties is by adding a conductive particle as graphene. So the aim of this work is to produce PEDOT PSS graphene composite. So we treated graphite thermically in N-methyl pyrrolidone. We sonicated it for more than 200 hours, and we obtained graphene in a dispersion. This dispersion was filtered, and we redispersed it in isopropanol. So we spin coated the graphene in glass substrates, and we also produced the composites with 50% of graphene in weight and 10% of graphene in weight. And we also spin coated this to produce the composite film. So these two tables synthesize what we did, the percentage, the way the films were spin coated. And we characterized it then by Raman spectroscopy. We measured the resistance by an adaptive for probe method, and we did scanning electron microscopy, UV spectroscopy, and atomic force microscopy. So the Raman spectra showed that the graphene was 2 to 5 layers, a few layer graphene, and we see that the redispersion didn't change the spectra. And also, I don't know if you're okay. Here we have the polymeric blend spectra, and we see that the spectra is altered after we add the graphene. This is due to the pi-pi interaction between the polymer and the graphene, showing the composites were formed. Here we have the results of transmittance and sheet resistance and conductivity, and we see that the films with only graphene, the three first, have poor results of conductivity, and these films are just PEDOT PSS. They are much better, but when we produce the composites, the results are even better. We also should see that the films that have more graphene have poorer results. This is probably due to graphene agglomeration. So what happens is that the high conductivity and electron mobility of graphene in a semiconductive matrix leads to better conductivity of the film. Here we have the microscopy, and we see that the graphene is well dispersed here. It is a graphene film without the polymer, but there is no conductive medium between the sheets. And this is why the films with only graphene have so poor conductivity. Here is one of the composite films, and we see that the graphene is well dispersed, but it could be more. And also, we should see that this is a film with 10% graphene. So the film with 50% probably really has agglomeration. Here are the atomic force microscopy results. We estimated the thicknesses of the films here. You can see here in the subtitle. And we see that when we add more layers of film, it gets more uniform, but it doesn't grow in a uniform way. When you add more layers, you have more thick layers each time you add more. Here we have the comparison between the phase image and a zoom of one of the composite films, and we see that those dark regions are soft regions, which corresponds to PSS, and the lighter regions are rigid regions, which correspond to graphene and PEDOT. So we have two phases, and the the conductive phase is interconnected. That's why the composite is much better than the other film. So concluding, we were able to produce and characterize the composites as we wanted. The transmittance and sheet resistance results are able to can make this material be used as transparent conductive electrodes. The redispersion of graphene in isopropanol was successful, and the pi-pi interaction between graphene and PEDOT and the transfer of electrons to PEDOT are responsible for enhancing the conductivity. Also, the Raman and atomic force microscopy showed that the composite was really formed. And here is just to show another possible application for this material as a conductive ink. We deposited conductive trail, and we were able to light up an LED. So this is another application for this material. And here are some of my references, and that's it. Thank you.
Thank you. Thank you, Mabilia.